So chapter 7 is kind of a doozy in terms of how many things there are to remember, but more importantly, there's going to be a lot of practice with this chapter, and the more practice you do, the better you get. But the whole title of it is one word, and it folds in nicely with our first note card, which is what is nomenclature? What is the title of chapter 7? Well, very simply, nomenclature is just a naming system. So it's a way for us to be able to know what compounds' names are, regardless of whatever the formulas are going to be. So let's do these three right here, PCl5. So we have three different compounds. They all have different names. For example, this one is sodium chloride. We named the first element, and then suddenly we have chlorine with an IDE ending. Here we have nitric acid. For some reason, this H tells me that this is going to be an acid, and this nitrate suddenly becomes nitric. And then down here we have phosphorus pentachloride. So very similar. There's a bunch of different rules. These are three types of three different examples, but all it is there's this governing body over all of chemistry called IUPAC, and they are the ones who essentially vote on and determine what the rules are for our naming system. So it's naming system for naming formulas and names. So we can either get a formula or we can get a name based on this nomenclature system. The information found in a chemical formula is really specific to just the number of atoms that are going to be bonded together. It doesn't matter if it's going to be ionic, covalent, or what, but it's relative to the number of atoms that are inside a formula. So I'm going to give you two different formulas here. The first one is C8H18. Now what the chemical formula here tells me two things. One, what are the atoms here? Well, we have carbon and we have hydrogen. The second thing tells me how much I have of each. So the subscripts here tell me I have 8 carbon atoms and I have 18 hydrogen atoms. So a chemical formula tells me the number of atoms and what type of atoms we have. So 18 hydrogen and we have 8 carbon. Again, the subscripts come immediately after the formula. So there's one more I'm going to give you that's a little bit more difficult to grasp, but the more we see it, the easier it'll get. Al2SO4 3. So what we have here is we have, of course, different elements here. We have aluminum, we have sulfur, and we have oxygen. It's very simple to start. There's 2 aluminums, so there's 2 aluminums. But the issue here is we now have parentheses and we have numbers inside and outside the parentheses. What the parentheses are, we can think of this like a math class. We have to distribute this subscript, or this says that not only do I have SO4, but I have it 3 times. So I can rewrite it SO4, SO4, SO4. We total up the number of sulfurs, we total up the number of oxygens, and that's going to tell me how much I have of each individual element. So from here, I have 1, 2, 3 sulfurs. So 3 sulfurs, or 3 sulfurs in total. And I have 4 plus 4 plus 4, which is going to be 12 oxygen atoms. So in this aluminum sulfate is what the formula is. Al2SO4 3. We have 2 aluminum, we have 3 sulfurs, and we have 12 oxygens. You can also think of this subscript as being distributed out this way, and we just multiply each one. 3 times, if I don't see a number, it's number 1. 3 times 1 is 3. 3 times 4 is 12. So we can find the number of atoms, and we can also find what types of atoms there are based on the chemical formula, whether there be parentheses or not. For us to identify the names and the formulas of compounds, we have to identify the 3 types, because the nomenclature comes from the 3 types. The 3 that we use are not new for us. Ionic, covalent are 2 that we had in the last chapter, but we'll now have a third one here called acids. And it's very simple for how we identify each one. Very simply, ionics are going to follow the same rules, and so are covalents that we used in the past. Ionics are going to have a metal plus a nonmetal. So an example of a metal and a nonmetal is sodium plus chlorine. That's going to be an ionic compound. Covalents are just going to be nonmetals plus nonmetals. So that can be something as simple as, what was our example before, PCl5. Phosphorus and chlorine are both nonmetals. That's going to be a covalent compound for us. Ionics, or more importantly, if we want to get into more specific details here, we're going to have ionic compounds being anything that have a positive charge or a cation, or a negative charge anion. added together. Covalents are all going to be sharing their electrons, so we can determine that in those different ways, but it's always going to be binary, or what that means is it's always going to be one nonmetal plus one nonmetal. Now, acids might seem a little intimidating because we haven't seen them yet, but it's very simple. Acids are anything that begin with hydrogen. So if I have a formula and it starts with hydrogen, it's going to be an acid. We'll get more into specifics later on, but for right now, that's going to be anything like HCl, HNO3, H2SO4. All of them begin with hydrogen, so those are all going to be acids. Again, ionics are metals and nonmetals, covalents are nonmetals and nonmetals, and acids are anything that start with an H. We use Greek prefixes only for covalent compounds. Now, we're going to spend the next few note cards talking only about covalent compounds, but again, those are anything that are two nonmetals put together. When we have covalent compounds, we're going to use Greek prefixes. So there's 10 of them. Each one represents a different number, and we will find out in our next note card how we use these. But very simply, I'm just going to write them and record them, as should you. So our first Greek prefix for the number 1 is mono, 2 is di, 3 is tri. These are all prefixes, so they come before any sort of words that might come afterwards. We have tetra for 4, and we have penta for 5, like pentagram. The rest of these are going to be very similar to your geometric shapes. So we have hexa, we have hepta, we have octa, we have, nona, and we have deca. So these are our 10 Greek prefixes. Again, we'll get into the rules for what these mean in a second, but they're only used when we have covalent compounds, which are nonmetals and nonmetals. We're just going to start by naming the covalent compounds. So that means if I'm given a formula, what would we say its name is going to be? It's very simple. There are 2 rules here. The first rule that we're going to have is you just name the first element in the formula using Greek prefixes to show how many atoms there are. So in this first example here, we have carbon. So we would just literally say the word carbon, and we would put in front of it the prefix that shows how many atoms. Our one exception here is if there's just one atom, we don't use mono for this first one. Just for this first element here. So because it's carbon by itself and we don't use mono, we just say that it's carbon, and then our second rule is we do the same. So we do the same thing. However, we drop the ending of the element, of the second element, and we add IDE at the end of the name. So we do the same thing. We use prefixes to show how many I have of that atom. In this case, there's 2 oxygen atoms. So I would use the prefix di, and then I name the element oxygen, but I add the IDE ending afterwards. So it would be diox. Instead of oxygen, we'd call it dioxide, carbon dioxide. We'll go ahead and do one more example that's kind of similar to this, where we have, we'll do down here. We'll have CH4. Again, carbon is our first element, and since there's only one of them, we don't add mono in front. And then we add the next element using its Greek prefixes. There's 4 hydrogens, so 4 is tetra. And then we drop the ending of the next one, and we add IDE, carbon tetrahydride. So that's what CH4 would sound like. To give you one that's a little bit longer, to make me write a little bit more, we can do P4O10, which would be tetra, phosphorus, deca, oxide. And it might seem weird, how come we have a decaoxide or decoxide? When do we get rid of some letters? Why do I drop oxygen at just OX? Why not I add the I, or the hydrogen? Why does it become hydride? You'll see that that's part of the nomenclature, and I'm not going to get into the specifics for each element, but you'll see as we start using them and you get them corrected, you'll begin to see that nitrogen becomes nitride, oxygen is oxide, hydrogen becomes hydride, etc., etc. So the more we practice, the easier it gets. So this one becomes very simple because with covalent compounds, the prefixes tell me exactly how many atoms I'm going to need. So if I have my first element here, or my first formula is dichlorine monoxide, If I wanted to write the formula for this, it's very simple. You just use the prefixes and you write the element's name. Again, the prefixes go with the element. So if I have dichlorine, that means I have chlorine. The di means I have 2 chlorines. Monooxide means I have 1 oxygen. It's as simple as that. It's very easy. The one thing I'm going to give you as a heads up for right now, if you haven't, or if you have seen the rules already, you'll see this and this will be more helpful. No crisscross. We'll get into crisscrossing later if you haven't seen this yet. But for these, it's very simple. Keep it simple. The prefixes just tell you how much I have of each element that comes afterwards. So I'll give you one more example here. We'll do sulfur pentoxide. Very simply, if there's no mono, there's no prefix in front of the sulfur, that means there's just one because we don't use mono at the beginning. Pent means 5, oxide means oxygen, so it'd be SO5. But again, there's no crisscrossing. We just use the prefixes to tell me. This is probably going to be one of our last very simple note cards. And we're going to keep it very simple to start with. If I want to name an ionic compound, what I have to do is just 2 steps. Let's say I want to do CAS. I identify that as being ionic because the first element here is a metal, calcium is a metal, sulfur there is a nonmetal. So I know that this is going to be ionic. What I have to do, first step, is just name the first element. Name first element. Very simple. So if I were to name this compound, the first element is calcium, so I just call it calcium. Second step here, I write the second element, so I name second element. But just like with covalence, we add the IDE ending. So if I wanted to do this one, CAS, it wouldn't just be calcium. It would be calcium. I would add the next element here, sulfur, but I add IDE at the end. No prefixes, no number indications to tell me what it is in the name. It's literally name the first element, name the second one with the IDE ending. It's very simple to start, which is very nice. So if I had, for example, Be3N2, what I would name this is just the first element, beryllium. And then I name the second element, but I add the IDE afterwards. Beryllium nitride. The ionics are very nice to name when there's no transition metals or when they're very simple ones. For the second part of this note card, we have to look at how are the formulas for ionic compounds written? Or more importantly, why is calcium sulfide just CAS? Well, what it boils down to is how many calciums do I need in order to counteract how many sulfurs? Again, ionic compounds are where they're going to be giving or taking electrons. And they want to give or take some more. For example, sodium chloride, NaCl, sodium has a charge of +1, or sodium, if I drew its outer shell, it has 1 valence electron. Chlorine has 7, 4, 5, 6, 7. It's very easy for sodium to give its 1 electron over to chlorine. The question is, what happens when we get other compounds or other combinations of elements? Calcium has 2 valence electrons, 1, 2. Sulfur has 6, 1, 2, 3, 4, 5, 6. Because sulfur wants to get to 8 and calcium wants to get rid of 2, it fits perfectly. 1 calcium for 1 sulfur. The issue comes when we have elements that have an uneven or an unequal amount. So for example, magnesium chloride, the formula is MgCl2. The reason is because magnesium has 2 valence electrons, chlorine has 7, which means it's almost full. This chlorine only wants 1 valence electron, which means this magnesium is still unhappy. It still has 1 it wants to get rid of. So what this magnesium is going to do is it's going to find a neighboring chlorine that also has 7 still, and instead of just giving its electrons to 1 atom, it's going to give it to 2. So this formula is MgCl2 because there's 1 magnesium and it needs 2 chlorines to get rid of its electrons. These chlorines are going to be happy and steal from there. So the ionic compounds are written based on what the charges are, or more importantly, based on how many electrons are going to be given or taken away. So what we have to do is I'm going to go ahead and give you just a formula. I'm going to give you a name, and we have to figure out what the formula is going to be. So if I had this formula or name, magnesium phosphide, your first step is you have to identify what are the 2 elements here and write their formulas. So magnesium is Mg, phosphorus is P. Second step is I need to write down the ion or the charges it is for each element. How I do that is I write them as a superscript up here, just like I do for finding out, other ions. So magnesium, what I have to do is I have to find magnesium on the periodic table. It's in group 2. So anything in group 2 has a positive 2 charge, and I literally write it out like this. For phosphorus, I do the same thing. Phosphorus is right here. It's in group 15, and your periodic table should also show you that that's going to have a charge of -3. What I need to figure out now is how many magnesiums am I going to need in order to counteract how many phosphoruses there are. Well, what we do for our step number 3 here is what I call the crisscross method. So what we do for step 3 is crisscross. Or a very simple way to do it is I can take whatever the charge is of magnesium and I can crisscross it and give it as a subscript for phosphorus, or it goes from the top left to the bottom right. So now it has 2 phosphoruses. If I were to do the same thing, this 3 on the phosphorus crisscrosses. Instead of it being an upper right on the phosphorus, it's now the subscript on the magnesium. And my final formula here is Mg3P2. Again, the charge is crisscross. That tells me not only what the charges are, but tells me what is the subscripts. We can prove this, and I'm going to go ahead and draw it just like I did before. Magnesium, there's 3 of them. Ooh, I might run out of space. Each magnesium has 2 valence electrons that they want to get rid of. The phosphorus, there's 2 of them in my formula here. Each phosphorus has 5 valence electrons, and they all, again, want to get up to 8. Magnesium wants rid of them. So we're going to start moving these electrons to the other atoms that want to make them a little more happy. Well, this magnesium can help out quite a bit. It can give this phosphorus 2 electrons, but it still only has 1, 2, 3, 4, 5, 6, 7. So it needs 1 more from another magnesium. That one's full. But now this magnesium here is unhappy. There's still 1 electron. So it's going to go ahead and find another phosphorus to give its electron to. But now this phosphorus is still unhappy because it has 1, 2, 3, 4, 5, 6. So it's until everyone matches up. In this case, it just needed 1 more magnesium. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Everyone's happy. 3 magnesiums to 2 phosphoruses. Again, the rules are very simple. I need to have the elements here. I need to have their charges up top. Again, that comes from the periodic table. And then I crisscross their charges to give me what the new subscripts are going to be. Our next few note cards are actually going to all be for the same thing. If I want to identify the formula for an ionic compound, what I'm going to have to do is I have to look at the charge of each element. So, for example, if I have to figure out the charge of an element here, I have to figure out what group it's going to be in on the periodic table. Again, the groups tell me what its charge is going to be. So, for example, group number 1, you should already have this written on your periodic table. Anything in group 1 has a charge of +1. Anything in group 2 has a charge of +2. We skip all these transition metals for a while. When we get to group 13, that 3 tells me I'm going to have a +3. Group 14 is going to have a +4. And then we're just going to start decreasing because, again, it's asking the question, do they need more electrons or do they want to get rid of them in order to have a valence shell that's totally full? Once we start getting to 15 valence electrons, it's easier to gain 3 electrons or gain 2 electrons for group 16, gain 1 for group 17, or gain 0 for group 18 because they're closer to that outer shell. So how are the charges of ions determined? It's going to be strictly based on what group they're in on the periodic table. It's as simple as that. So make sure you have that recorded. Now is the time for the transition metals. So we have Roman numerals here to identify charges of transition metals. You might have asked this question in class, you might have noticed this in class, but when we figure out the charges of all the elements on the periodic tables, the group number tells me the charge, +1, +2, +3, +4, but we suddenly miss all these transition metals. The reason is because they're so good at conducting electricity, as metals normally are. They're so good, electricity is the movement of electrons. They don't hold on to the same number of electrons every time. They're going to be okay with giving them, so they basically have multiple charges. For example, copper is a great example. It can have a +1 charge, but it also appears in the environment as a +2 charge. So I can't just write a charge above copper here on the periodic table because it's not going to work because it is fluid and there's multiple options. So what we use instead is we use a Roman numeral every time we're given a formula if there's a transition metal in it. Once there's a transition metal with the formula, then that's going to tell me the charge, and the charge tells me what Roman numeral it's going to be. So the Roman numerals, again, if you don't have them, they're very simple. I is 1, 2 I's is 2, 3 I's is 3, but then we have IV for 4, V for 5. I'll just go up here. VI is 6, VII is 7, VIII is 8, IX is 9, and then X is going to be 10. There's not going to be any more Roman numerals than that, but we use those whenever we're going to use an ionic compound. So it's ionic with a transition metal. So we're going to do some examples here so that we can see them. The first example I'm going to give you is I'm just going to give you the name, and we can see what those Roman numerals mean. So for example, this first one here, we're going to do iron, which is a transition metal, and we throw the Roman numerals in here afterwards. Iron 2 oxide is how we say it. What this means is this transition metal, iron, has a charge of 2. So if I want to write the formula, we do the same steps as before. Write iron, write oxygen. Then we have to write the charges. The Roman numeral automatically tells me what the charge is going to be. So this charge is going to be a +2 on that iron. And then we look at our periodic table and see oxygen is in group 16, so it's going to have a -2 charge. And if I want to write the formula, we do the same rules as before. We crisscross our charges, and we're left with Fe2O2. But again, we can simplify if we need to. The 2's are the same number, so they can simplify out, and we're left with FeO. This is the formula for iron 2 oxide. Even though there's not a 2 in the final formula, because it's simplified out, they are still the same name and formula that match up together. So if I want to do the opposite, if I want to go ahead and be given a formula first, how would I figure out the name? Well, let's go ahead and do, let me write in a different color here. Let's do CuCl2. What we have to do is we have to write the elements' names. So copper is the first one. Oops, it's a transition metal, so we have to have Roman numerals. And then I add chloride at the end. Same normal naming system. I'm sorry, that's a little cut off. But what I have to do is figure out what Roman numerals go with the copper. Over here, with the iron 2 oxide, we had to crisscross the charges to figure out our subscripts. Well, for copper chloride, if I'm given the formula, we reverse it. I know what my final formula is, so if I can figure out what the charges were when they crisscrossed, if I can reverse crisscross them, that will tell me what the charges are, and whatever number is above the copper is what's going to be the Roman numeral. So if I reverse crisscrossed it, under this copper, if I don't see a subscript, we automatically assume that's a 1, and we bring that up here, and we say chlorine has a -1 charge, which it should. If you look at your periodic table here, group 17, it's going to have a -1 charge. So that checks out. That means this is working. So that means, where's this 2 come from? Well, this 2 was crisscrossed and given from the copper, a +2 charge. It gave the 2 down to this chlorine, which means this copper has a copper 2 charge. If I were to do the same thing for one more example here, I could do something like CuCl. Again, it's copper and chlorine, but it's going to have a different Roman numeral. It's going to be whatever Roman numeral it gave to the chlorine. So what number is down here? Well, if I don't see a number, that means it's always number 1. This is the number 1. Chlorine is always having a -1 charge. It crisscrossed from this. That means this also crisscrosses if I don't see it, and that means this copper had a +1 charge. Both the same elements, copper and chlorine. It's just one has a different Roman numeral. That should be a 2. Based on what its charge is going to be, what its charge was initially. So the Roman numerals are just for transition metals, and it's just for ionic transition metals, and the charge is shown by the Roman numeral. The charge of the transition metal is the Roman numeral. There's going to be a good amount of rules for Notecard 10 here, so give yourself some space. But we're starting now with acids, the new type of compound for us. Again, acids are anything that start with a hydrogen ion, or anything that, like HCl, starts with that hydrogen as its first ion in its formula. So how do we name acids that don't contain oxygen? Well, very simply, it's just like HCl, the first one, no oxygen. We'll label it kind of here. No oxygen is the first one, like HCl. What we're going to do is we're going to write the name hydro every single time. I'll put it in quotation marks so we see it. Hydro blank, and you write the element here, and we add the ending ICAL. acid. So for HCl, if I wanted to write HCl, what I would write is hydro. I write the element that comes afterwards, chlorine. So I'd write chloric, add that IC at the end, acid. Hydrochloric acid. Again, this is if there's no oxygen in the formula at all. HCl, no oxygen, hydroic acid. Our next one is what happens if they do contain oxygen. And there's a good amount of rules for these. We call these oxyacids. So the oxyacids are if there is oxygen in the formula. Now there's a couple different options of this. I'm going to make it very simple now. We'll see the practice on the next note card. But it all depends on what the prefixes are in those oxyacids or in the formula before the hydrogen. So we have if it ends in ate is a rule. If it ends in ite, there's a rule. If it ends in hypoite, or if it has per ate as its prefix and suffixes. There's going to be different rules. So I'm going to keep them very quick, very simple, so we can see the examples and you can get them recorded. Our first example here is if it ends in ate, it becomes ick. So an ate would be anything like HNO3. We can ignore the hydrogen here and we just look at what follows. NO3. Well, hopefully NO3 looks pretty familiar to us. It should look like some of our polyatomic ions. All of these oxyacids are polyatomic atoms. That's why I said it's very important to have these from chapter 6, because an oxyacid is anything with a hydrogen and then a polyatomic ion that follows. So this one is nitrate. NO3 is nitrate. What we would say to name these is if it ends in ate, all we do is we write the polyatomic atom, so poly, we write its name, but we drop the ending of ate and it becomes ic acid, similar as above. So if I were to rewrite this one here, I would rewrite this one as just nitric acid. Simple as that. Drop the ate and it becomes ic. Now, ites are going to be very similar to this, and I'll just give you this example here. We'll do something that looks similar to NO3, but it's NO2. NO2 is what we call an nitrite, ends in ITE. We'll get in the nitrites here in the next note card. But what we do for naming is we say the name of the polyatomic ion, and instead of saying ic at the end, we say us acid. So in this case, instead of being nitric acid, like our previous example, this would be nitrous, OUS acid. Hypoites go one step further, where there's one less oxygen here. So instead of NO2, it would be NO1 or just NO. What we do here is we keep the hypo. So this is hyponitrite. NO is just hyponitrite. We'll get into that again in the next note card. But we write hypo. We keep the prefix hypo. Hypo. Write the polyatomic. And then we add us again at the end, just like with the ite ending. So this one would be nitrous acid. Hypo and the us stays, and we just use the polyatomic name base. Now we go to the pers and the ates. That's if I have one more oxygen than the ate, or what I start with. So NO4, we call that pernitrate. So what we do for these is we say per still. We name the polyatomic ion, and then we add ic, just like with our ates at the beginning. So if I were to do that and write this, this would be pernitric acid. I'm hoping you can start to see some of these patterns. We'll get into more of them here in a little bit. But if it's an ate, whether it be per ate or just ate, it's going to end in ic. If it's going to be an ite, it doesn't matter if it's ite by itself or hypoite, it's going to end in us. And then if it has a prefix, prefix like hypo or per, we keep the hypo and we keep the per. There are rules again, but the more that we practice, the more that we see them, and the more that we identify our polyatomic ions, the easier this is going to get. That's why I said it's very important for us to have those polyatomics. This note card is very simple in premise, but it's a little bit harder in practice. But again, I'm going to put this up at the top here. This is all based on our polyatomic atoms. So polyatomic atoms, or polyatomic ions, are going to be anything that have oxygen in them, or they're going to be two covalently bonded molecules that have a charge at the end. Most of these, when they become acids, are going to have oxygen in them. And we need these in order to name an acid. So it's very important for us to know the ates, the ites, the per-ates, the hypoites. But more importantly, it's all from the polyatomic ions. As we do our polyatomic ions like C2H3O2 minus 1 charge, or we get sulfate SO4 2 minus, they all end up having the same suffix there, if you noticed. This is acetate, and this is sulfate. They all end in ates. All of the polyatomics that I had you memorize so far all end in 8. Those are our base polyatomic ions. To go from per-ate to 8 or 8 to per-ate to ite to hypoite, all we're doing is on this spectrum here, we're either adding more or less. Now it's more or less oxygen. So in the formula, if I have more or less oxygen than my base, then I'm going to end up being per-ate. If I have less oxygen and I move to the right of the spectrum, I'm going to be ite. If I lose 1 oxygen, if I lose 2 oxygens, it's going to be hypoite. So I'm going to give you an example with all of these here all recorded. So if I have carbonate, CO3 2 minus, that's carbonate. If I start losing oxygens, I can start rewriting them as CO2 with a 2 minus charge. It keeps the same charge. The only thing that changes is the number of oxygen atoms I have. If I do the same thing one more time and I lose 1 more oxygen, I still keep the same charge, but it's now CO2 versus CO. If I add 1 more on the other end, CO4 2 minus, it's now gained an oxygen, keeps the same charge. The names are what changes. They keep the same root, carbonate, but instead of being carbonate, it becomes carbonite, and then it becomes hypocarbonite, based on whether it lost 1 oxygen or lost 2 oxygen. Now, if we gain 1 oxygen, we go from carbonate, we add the prefix per carbonate at the beginning, and there we go, we have our new name. This is percarbonate, this is carbonate, this is carbonite, this is hypocarbonite. You can start seeing some of the patterns here. The last thing that I want to show you and be very clear about showing you is where these prefixes come from. Where do you think the word per and hypo come from? Well, if you have hypothermia, you have less heat. Hypo meaning less heat in your body. Hypo means less, so we lose 2 oxygens. Lose an oxygen, or we lose 2. Per is just like hyper, which someone is hyperactive. They have more energy than someone else, more activity. Hyper means we have more oxygen, so it's going to have 1 more oxygen at the start. Again, this is based on the polyatomic ions, so if you don't feel comfortable with this, you need to go back 1 step and you need to get comfortable with those polyatomic. Okay, here are some examples. I'm going to start throwing stuff out at you, and I want to see what we can start doing here. Again, practice gets us better at all of this. So I'm going to go ahead and start with the first one. How do we write the formula of any types of acids? So our first one we're going to try and do is hydro. We'll do hydronitric acid. And our second one we're going to do is just persulfuric acid. I'm kind of throwing you under the bus right away. So the different types of acids are either binary, where it's just hydrogen and 1 other element, or we have hydrogen, 1 other element, and an oxygen, or there's an oxygen in there somewhere. So how this works, how this is going to be done, is we have to do this first one. Hydro, we should look at our note card number 10, and we see that hydro is the prefix for no oxygen. So all we write is hydrogen up front, and we add the element that comes afterwards, nitric. Well, the root word for nitric is nitrogen, so we write HN. Sweet. Now the question is, where do the numbers come from? Well, we still have to do the crisscrossing in charges because these are ions. Hydrogen has a +1 charge, nitrogen on your periodic table has a -3 charge. We still have to crisscross. That 3 goes down there, that 1 goes over there, and we're at H3N. Hydronitric acid. Hydrogen, no oxygen, H3N. Now, if I go to the other side, I do something very similar. The issue is I know that because there's no hydro, that means there is oxygen. So I have hydrogen and I have an oxygen. What number or letter goes before the oxygen is based on the polyatomic ion regardless of the suffix or prefix here, I have sulfic, which means it's sulfur, and I add an oxygen because there's no hydrogen. Now the question is, where do the numbers come from? Well, per sulfuric acid, the per-ic tells me that it's per 8. And again, per 8 tells me I have one more oxygen than whatever our root polyatomic ion here is. So if I have sulfuric, sulfate is our base, which is SO4 2-, and we just have that memorized because it's one of our base polyatomic ions. Per 8 means I have one more oxygen here, so instead of it being SO4 2-, the per 8 version is SO5 2-, one more oxygen. So I would just literally write the same thing here, SO5 with a 2- charge up here. Now this is a polyatomic ion, so it's going to be together by itself, so that 2 charge doesn't go anywhere except outside the parentheses. It's not with the sulfate, it's going to now be with the hydrogen. So if I were to rewrite this, be H2SO5. Now hydrogen does have a +1 charge, and it would go to the outside of the parentheses. However, we don't have to rewrite it. Just like with our hydronitric acid, we don't have to include that +1 charge. But these are the 2 ways to write the formulas. Again, it's all dependent on, do you recognize hydro means there's no oxygen, and if there's not hydro, it means there is oxygen. Then we have to relate back to the period or our polyatomic ions, and then the different prefixes and suffixes, whether it's going to be ite, ic, or whatever it's going to be.